Okay, so here we go with, what is this? This is section 4.8. The title of section 4.8 is differentials. So in this section, what we're going to take a look at is we're going to take a look at this idea of a tangent line to a curve as an approximation tool. We're also going to take a look at the idea of the value of the differential, dy, and the actual change, compare and contrast how those things occur. We'll see how this relates to the idea of propagated error, and then we'll take a look at finding the differentials of a function using the differentiation formulas. Okay. All right, so here we go. Tangent line approximations. Now, we have been doing tangent lines in this class since, jeepers creepers, way back at the beginning of the semester. One of the first things we did when we started talking about calculus is we said, hey, one of the big things in calculus is being able to find the instantaneous rate of change of a curve and then use that instantaneous rate of change of the curve to talk about the tangent line to a curve. All right, so consider a function f that is differentiable at some value c. Then the equation of the tangent line that goes through the point c comma f of c is going to be y minus f of c is equal to f prime of c times x minus c. That would be x minus c, the quantity. That's just the slope formula. That's just plain old y minus y sub 1 is equal to m times x minus x sub 1. We're just replacing this with the f of c to give it the y value. We're replacing this with the value of the derivative. We're replacing that with the c value. It's this picture right here where you have some function. In this case, we have the square root function. So this is the function f of x is equal to the square root of x. And we're drawing in a tangent line, okay, at some point c. All right, so here's where tangent line approximations start to have value. There are many, many functions out there, square root function being one of them, but there's lots of them out there, that do not play well with most input values, right? The square root function, f of x, it plays well with a lot of numbers. For example, what is f of 9? Well, that's going to be the square root of 9, which is 3. That works well. F of 16, square root of 16, that's 4. It works well. But there's lots of numbers that it does not work well with. For example, what is f of 2.5? That's the square root of 2.5, and the answer is I don't know. Now, I could punch this up on my calculator and get some sort of a decimal approximation, but how is the calculator doing that? How is it coming up with the decimal approximation? I mean, it would be unrealistic to assume that someone programmed in all these values and that it's just recalling these values from memory. It's figuring it out somehow. And what it's doing is it's using a more complicated version, a more complicated example of what we're going to do right now. So what we're going to do right now, though, is we're going to do something called a tangent line approximation. And the argument that we're going to make is that because the tangent line is close to the curve for values close to c, so for some interval here, for some interval that's going to be from c minus a little bit, and we're going to call that little bit, I don't know, maybe a delta x, to c plus a little bit, that tangent line is close enough to that curve that if we use the tangent line as an approximating tool, that it won't be off by that much, and that it would be a reasonable approximation. So that if I wanted to find the square root of 2.5, I would just take that 2.5 and put the 2.5 into the tangent line, so 2.5 into a tangent line, and then find out the value of the tangent line at 2.5 and say, that's close enough, okay? Now, the key here is, though, the trick here is, the important thing that we need to be able to do is we need to be able to find this point, the point c comma f of c, the point where the function plays well with a number. So we need to find a c that works with the function, okay? And then we can draw the tangent line there. So what's going to happen here is we are going to make this argument right down here. We're going to say that as long as we're close to that nice point, the value of the function can be approximated by, and if you look at this carefully, this is the tangent line. Okay, this is our tangent line with this piece moved to the other side, where it just then becomes y equals f of c plus f prime of c times x minus c. And that's where we get this equation right here from. Okay. Now again, this is all predicated. This is all hinged upon. We can find a number c to put here, here, and here that plays well with our function. Right? And then what you're going to do when you get to Calc 2 is at the end of Calc 2, you're going to say, well, wait a second. And let me get rid of some of this extra stuff that we don't need here anymore in this drawing. If a tangent line is good, what if we could find, instead of a tangent line, what if we could find maybe a parabola that was around that point that fit the curve for a bigger interval? Or what if we could find maybe a cubic equation that fit it for an even bigger interval? Or what if we could find a fourth degree equation or a fifth degree equation? And what you'll start to do is you'll start to develop these, and they refer to these as Taylor polynomials, and you'll do this at the end of Calc 2. These polynomials that model the function reasonably well for an interval around a value. So when you type in the square root of 2.5 on your calculator, the calculator isn't finding the square root. The calculator is using some sort of a polynomial, okay, which a tangent line is just the simplest one because it's just a line. Okay? It's using some sort of polynomial approximation tool. Now, I contacted TI at one point in time and asked them, what they actually use, what kind of equation they use, so when I teach this lesson, we could talk about it. And they wouldn't tell me. They said it's proprietary. I'm like, okay, I get it. But that's what you're going to study at the end of Calc 2. So we're going to take a look at the simplest example, a linear approximation. If you want to get fancy about it, we are going to find a Taylor polynomial of degree 1. Okay? All right, so here's our example. We are going to find a tangent line to approximate the square root function, and we're going to use that then to evaluate the square root of 3.98 and the square root of 4.05. Okay? And luckily for us, someone has done the legwork and they have said, here's a number c, 4, that is close to where we want to take those approximations and also plays well with the function. Okay? So what we need to do is we need to say that f of x is going to be approximately f of 4 plus f prime of 4 times x minus 4. Now, where did that come from? That's just this plugged in, right? Okay, so let's review really quickly. I've got a function, square root function. It does not play well with most numbers. In fact, I don't know how to find the square root of 3.98 by hand. Okay? I don't know how to find the square root of 4.05 by hand. So what I'm going to do is I'm going to approximate the square root of 3.98, and I'm going to approximate the square root of 4.05 by drawing a tangent line to the curve f of x equals the square root of x at the value, at the point when x is equal to 4. And we call that value c. I don't know why, that's just the letter we use. Okay? This is going to be the formula I'm going to work with. Okay? I need to know two things to make this thing work. I need to know f of 4 and f prime of 4. Well, f of 4 is pretty straightforward. F of 4 is just the square root of 4, which is 2. Right? F prime of 4. Well, before I can even find f prime of 4, I need to figure out what f prime is. So over here on the side, what is f prime of x? Well, f of x is the square root of x, so f prime of x is going to be 1 divided by 2 root x. Okay? Now, if you're wondering how I did that so fast, I have taken the derivative of the square root so many times I know the answer. Hopefully, you're there too. But in case you need to see the steps, rewrite with a fractional exponent. Take the derivative. Negative exponent means it goes in the denominator. And so we get that. So then what's f prime of 4? Well, f prime of 4 is going to be 1 divided by 2 times the square root of 4, which is 1/4. And now we have the statement that f of x for values close to 4 can be approximated by 2 plus 1/4 times x minus 4. Right? So if I want to find f of 3.98, that's going to be approximately 2 plus 1/4 times x 3.98, so 398 over 100, right, minus 400 over 100. Now, if you're wondering, why am I doing this right here? What am I doing here? You have to remember where this came from. The purpose of this is to be able to evaluate functions by hand, because that's when this stuff was developed. I didn't have a calculator, so I wanted to find the square root of 3.98, so I'm going to approximate it by hand. Okay? So I'm going to do this entire problem by hand. So then this is approximately 2 plus 1/4 times 398 over 100 minus 400 by 100 is negative 2 over 100. It's approximately 2 plus, let's see, that's what, 1 over 50. Minus, I should change that from a plus to a minus. We'll distribute that negative. Minus, let's see, what's 1/4 times 1 over 50? Is that 1 over 200? Well, 2 is what, 400 over 200, so 399 over 200. Okay? All right, so I'm going to bring something up here. Let's see how this works out. Just going to use my calculator to see how close we are. So what does TI think? TI thinks that the square root of 3.98 is 1.994999. And we got 399 divided by 200. 1.995. So we are, if we round TI's answer to 3 decimal places, we're spot on. So tens, hundreds, thousands, we go down to thousands place for a by-hand technique. Now, as I said earlier, if you didn't think that this was accurate enough, if you want a greater accuracy, well, where's the error coming from? Well, the error is coming from how far apart those two things are. So I know that this is not to scale because that's 1, 1 over there, but just pretend for a second that this point right here was the point 42, which is the C we're using down here. Right? So then 3.98 somewhere over here. And the tangent line is a little bit above the curve. And that difference between the point that is on the tangent line and the actual value, that difference is why we get 1.994993734 and 1.995. This little tiny difference is where they're off by. Now, if you wanted that to be smaller, you have two options. You can either bend this tangent line and make it not a line, make it some sort of higher power polynomial function, or the other option is move this point C closer to 3.98. Now, if you had nothing else to do all day, if you were just sitting there doing math all day long, do you think that you could find some fraction that is closer to 398 hundredths that is a perfect square? So it would play nice with the function, because if you could move this point over closer, say to here, then this difference would get smaller and your answer would be more accurate. Right? So I don't know what that number is, but I'm pretty sure there's a number between 4 and 3.98 that is a perfect square, considering that there's infinitely many numbers in between those two. And if there's infinitely many numbers, I can find a perfect square. If I can find a perfect square, I can make a tangent line there. If I can make a tangent line there, then I can get a more accurate answer. Now you might be thinking that's a lot of work. Yes, it is a lot of work. But back in the day, when you didn't have a calculator, how else did you find this? Right? Now we're almost done. We still have one more to do. We haven't done this one yet. Right? So we want to do square root of 4.05. So we want to find f of 4.05. Well, that's going to be approximately 2 plus 1/4 times 405 over 100. I'm just converting it to a fraction right away. Minus 400 over 100. Okay? It's approximately, let's see, what's that going to be? 2 plus 1/4 times 5 out of 100. 5 out of 100 is 1/20th. Okay. 2 plus 1/80th. Let's see, 2 and 8 is 100, so 161 over 80. All right, let's bring the calculator back up and try it again. What does TI think the square root of 4.05 is? It thinks it's 2.01. And what's 161 divided by 80? 2.0125. Rounded, we have the same answer out to tenths, hundredths, thousandths, 10,000ths place. Now, I don't know about you, but I think this is pretty amazing. Okay? I can find a function that is easy to evaluate. Now, remember, when I say the word easy here, you might think that these fractions are a pain to work with. But I would rather do this than try to use some sort of guess and check method to find the square root of 4.05. And if I don't have a calculator, this is pretty magical that it can find me an answer reasonably close enough that I can make this thing work. I'm very pleased with the ability of this as a tool. Okay? All right, so these are tangent line approximations. This is our next example. I'm going to come back and make a second video, and this will be our first example for our second video.